People are doing good. Today, we will start a new topic that is basically on Exergy or available and unavailable energy. So, till now, I hope you all have watched my previous lectures, and I have also made the playlist of thermodynamics that will be completed soon. So, if you haven't watched my previous lectures, I would recommend you to watch them before watching this lecture so that you can gain more knowledge from this lecture. So, without further delay, let's start. So, available energy and unavailable energy. So, available energy is the maximum amount of work that can be extracted from a certain heat input in a cycle. So, Uh, suppose you are doing giving some input to an engine and expecting some output. Uh, the available energy is the work output that is the maximum that you can get by a particular input. So that is available energy that you can uh, take out. And similarly, one more term is there, unavailable energy. It is a minimum amount of heat that has been rejected to the sink. So, when you will be having the maximum work output from a certain input, then the energy that goes to sink, like if you already have taken the maximum work output, so the left energy is unavailable energy. So that is the minimum amount of heat that should be rejected or is subtracted from the input heat. That makes the unavailable energy. So again, you must have seen this many times in my previous lectures. So this is first law and only conserving the energy. So this is basically the efficiency of this heat engine. Since you can see the temperature in the formula of efficiency, this means this cycle is for reversible only. Okay. So if TL is constant and TH is increased, TH is higher, TL is lower reservoir temperature. So efficiency will increase, and if TH is constant, then TL should be reduced so that to increase the efficiency. And up to this limit, this can be reduced, not lower than this. And this level, this can be increased. Like limitation here is the turbine blade temperature which turbine blade can sustain. You cannot go over the temperature limit of the turbines. So this is the TS diagram for this particular cycle. So this is efficiency and uh, W max is this. So W max equals to Q1, that is the input heat, and this is the efficiency of the cycle. So this into this gives you the maximum work. And why I'm saying this is maximum, because this is for reversible, because we are using temperature term here. Okay, so W max is this, and you can rearrange it like this. This is Q1 by T1, can also be written as delta S. I have discussed this in my previous lecture on entropy. So you can watch this if you have any doubt regarding this. So this is the final formula, Q1 minus T naught delta S. T naught is the ambient temperature. So this is basically available energy, Qs minus Qr, input minus rejected heat, and rejected heat is also can be used as unavailable energy. So unavailable energy, like after comparing this to this and this to this, so you get unavailable energy as T naught delta S. So we have a question here. 1000 kilojoule of heat is supplied to a reversible heat engine from a source maintained at 327 degrees Celsius, and the sink temperature is, so this is T1, this is T2, then determine A and UA. So you know T1, T2, then you know efficiency this by this formula. So efficiency would be half. So you know W max, this is the available energy, and unavailable energy is Q input or input minus the maximum work or the available energy, that is unavailable energy. Okay, this is a simple question. Again, let's start with theory only. So, loss of available energy when the same heat is transferred through a finite. So, here the heat engine was working reversible in a reversible manner. So, you do not see a finite temperature difference over here. Like the reservoir is at T1 and we are getting the heat at T1. So there is no temperature difference because it is a reversible process. But we'll be discussing here about the when we have a finite temperature difference. That is, uh, we are getting heat at from reservoir at T1, but uh, the system is at T2, so we are getting heat at T2, like absorbing heat at T2, correct? So then we cannot write efficiency in terms of temperature directly because it is not a reversible process, because here we have finite temperature difference. So efficiency would be output by input divided by QS. So this is a final formula for efficiency. So when QR is constant, QR is basically rejected heat. So QR is constant and QS will be increased, then efficiency will be increased. So here is the temperature difference you can see. So from where we are taking the heat. So Q2 should be as high as possible to increase the QS, so to increase the efficiency. And if we take Q1 is equal to Q2, then this means that T1 into delta S should be equals to 2 into delta S dash. So Q1 equals to Q2. T1 is greater than T2, then delta S dash should be greater than delta S. So here you can see delta S is greater than delta S dash. So if this is happening, then you must be able to see from the graph that here is the additional loss in the energy if we reduce the temperature of from like the temperature at which we are taking the heat from the reservoir. So if we reduce that, then there is an additional loss in the energy. So efficiency will be decreased. You can see it from there. So Q1 at T1, if we take heat directly at T1, then that efficiency will be greater than that the efficiency that we take at T2, because here we are taking the heat supplied to be equal. Therefore, the entropy change will be there, and due to the entropy increment at lower temperature, the heat losses are more. So the available energy will also be lesser in the case when we take heat at T2 and then T1. So in that scenario, increase in unavailable energy will be T naught delta S test minus delta S, the shaded portion that I have showed in the graph. That is this. So Q1 equals to T1 delta S, then delta S equals to Q1 upon T1. This is from previous lecture of entropy. Similarly for S2. Then we can write this as this. So here you can see that both Q1 is taken for T delta as T2 delta S because Q1 and Q2 are same for this case, as I've told you earlier. So it can be written as this also. And increase in unavailable energy can be written in this form. Okay. So increase in unavailable energy or loss in available energy, the final expression for this is this. So you can derive it if you have got the concept. So it is important to got the concept so you can derive it also in the future. Greater the temperature difference, more will be the loss of available energy. Therefore, some heat is having more importance. Same heat is having more importance at higher temperature in comparison to the lower temperature. You can see from this that if you take same heat at higher temperature, that would be more beneficial because the heat losses will be lesser in the case when you take the same heat at higher temperature rather than the same heat at lower temperature. So this point is basically signifying the same derivation and the same conclusion that we have derived just above. So availability, it is a maximum useful work that can be obtained in which the system comes in equilibrium with dead state in a process. So the difference in the case that we discussed just above is we are not considering the final state as the dead state. It can be any other state also other than the dead state. So dead state is basically coming to atmospheric ambient or surrounding temperature. Okay, so let's discuss it for first for the closed system. Uh, Useful work is TdS equals to du. This is the first law of thermodynamics that is rearranged from my previous lecture that is on entropy. So PdV is useful work for closed system. So if you take it to the left and the shuffling, then you get this equation. So this basically TdS minus du. And if you are talking about the dead state, so for dead state, SF will be S naught directly, Si will be S1, that is the initial state, and same for U final will be U naught and U initial will be U1. So, so maximum useful work is can be not maximum, but yeah, useful work can be written as this for closed system. Uh, so same thing is there. Uh, this is the same equation that we have just derived above. That is useful work for the closed system. Now there is another concept of maximum useful work. So in case of maximum useful work, like the pressure work is also considered because while expanding or anything that is happening either compression expansion, the some volume change is there, and the volume change exerts some like the pressure outside is P naught, and if we increase the volume, then there is some work on the outside system. So this work can also be utilized. So if we also consider this work, then this useful work becomes maximum because we are using uh, all the useful work from everywhere we can use. So that becomes maximum when you use the pressure work also. So on rearranging this, we get this. So this is basically the same thing. So this is maximum useful work for closed system. Don't confuse this maximum useful work with useful work. Here we have not considered the pressure work. Okay. So let's come to uh, open system. The earlier case we have discussed was for closed system. Now we will be discussing about the open system. So useful work is this for open system. Instead of U, we use H because there is flow work also. So H comes here. And this I have discussed in my first lecture also, where I have write the work for open system. So you can use it for a reference. And here the maximum useful work is same for closed and open both. Expression of useful work. And maximum useful work is same for open ecosystem. So yeah, you can remember this as important point. Low availability and or availability function. So change in availability function represent the maximum useful work. So for closed system, maximum useful work is basically this. Uh, we have discussed it just now. This is same as this. So if you rearrange it, then you can write it in this form, and this is written as this as phi 1. You can see it from here. So all this I have discussed in my first lecture only because like phi 1 is a function that is represented using the state in this. So summing up all the terms makes phi 1. So the subtraction of this gives you the maximum useful work or a closed system. Similarly for open system, this is uh, for open system. We represent used to present it like psi, but here we have used only pi only, so it's fine. Don't confuse it with these both things are different. Irreversibility is the defined as the difference between the maximum work and the actual work. So uh, whenever there's irreversibility, so the work output that we get or the useful work that we get, that is always lesser than the maximum useful work. So the difference is represented by the uh, between the maximum work and actual work is always represented by this irreversibility. I have discussed in my this in entropy lecture, like where I have told that the irreversibility is the reason for reducing the work output or efficiency of a cycle. If the same cycle is reversible, then there would be no difference between these two things. So there is one important theorem, that is Todola's theorem, Gauss-Todola's theorem. According to this theorem, the rate of the reversibility is directly proportional to the rate of entropy generation. So this is represent mathematical representation of this above statement. DS can be simply summation of the system plus surrounding that constitutes the universe. So this equation is pretty simple. Let's discuss about one machine named PMM, Perpetual Motion Machine 2, that works on the violation of the second law of thermodynamics. So, so it says that it is impossible to make a machine that violates PMM2, that violates second law of thermodynamics, or it implies that complete conversion of the low grade energy into high grade energy is impossible. Like you need a reservoir or a sink that takes like that where we reject some heat to get some work output. So you cannot convert all the heat to the work all the Similarly, PMM3 is also there. It is impossible to correct construct a device run completely in the absence of friction. So you cannot uh, avoid friction anyway. So perpetual motion machine violates third law. So and here this third law of thermodynamics. It is impossible to achieve absolute zero Kelvin temperature in a finite number of processes. So you cannot achieve zero Kelvin temperature by any process and any number of cycles. It is impossible to achieve. So this is pretty simple and pretty straightforward. So no need to go uh, there's nothing much about this in numericals also. So let's discuss Nernst equation, Nernst assignment statement. Uh, the entropy of a perfect crystalline substance is zero at absolute temperature. So crystalline substance are generally that occur in nature, uh, like by natural nature, by natural only. Okay, there is no artificial. We do not create it by our own. Like that is that occur in nature by nature only. Okay, so we take their entropy uh, uh, as zero at absolute zero temperature. But there is nothing like absolute zero temperature. I discussed it here. Compressivity factor. This factor is important while dealing with real gases. So it represents a deviation in the behavior of actual gases that are real gases from ideal gas. So the mathematical representation is this, that equals to PV upon RT. That is equals to 1 for ideal gas. That that is never true for real gases, and it can be either less or greater than 1 for real gases, depending upon the conditions. One more thing is there, Gibbs function or Gibbs the energy. So G equals to H minus Ts. This is the Gibbs function. Uh, and dg can be written as like this, dg direct differentiating differential of dh h tds. Here we are taking like using chain rule while differentiating. So uh, this I have told you earlier in this lecture also, and in my previous lecture on entropy also. So tdf equals to th minus vdp, and we substitute it in the above equation and we get this equation. So during phase change, temperature and pressure both are constant, so dg will be equals to 0. One more function is there, Gibbs Helmut Helmholtz function. This is not very much important, but just for the knowledge and awareness, you can read about this. So change in Gibbs Helmholtz function is equals to this is Gibbs Helmholtz function. So change in this can be written like this, just as we did it for this function. So we are using this here we have used it in this format, and here we are using with the help of du and bdp. So upon manipulating this, we get this. So this is just after doing some manipulation, you get this equation. So this was all about this lecture. Hope you all liked it and gained some really insightful knowledge. And if you really think that you gained a lot, so please like, share, and subscribe to my channel, and subscribe and